cold, a little bit of snow, and then also just a hectic morning. Stuff just was not working the way it's supposed to. All right, we got volume, we got video, we're rocking. And we're charging ahead on our last required module. So looking at linear algebra and how to solve these kind of problems with here. Mostly we're using like NumPy. SciPy is kind of the general term because there's a NumPy linear algebra package and a SciPy one. There's a lot of overlap, like they both have solve functions. Some of them have, sometimes SciPy has more options than NumPy, but that's our main thing. Have you gotten to the part with using linear regression again? So rather than using, I mean, PolyFit uses linear regression same way that we're doing here, but you can have like generalized linear regression. So it's not always straight line fits, it's the fact that the constants can be separated from the function itself. Any questions or like troubleshooting coming up so far? Yeah.
Can we look at the project today?
Oh, looking at project?
Yeah, because I think that's the next due.
Yeah.
So this would be the only class we're posting. So if we could like go over it.
When is it due? All right, let's do a quick. Because I know we shuffled things around, and I don't know if Project 4 has been updated for that. All right, let's double check or rebounce everything to. Project 4, oh, homework 4. Let's look at month. October, oh my God. Yeah, but we have a whole nother week. To do this. We gotta shift this one. Let's send it over to like Thursday next week. Yeah, so we can spend some time on here. There we go. 20th, yeah. So that'll give us a couple more classes. Take a look at it. All right, I think that'll be better. Take some time, actually get some time to think about it and put some work in. anything, so like turning in homework for, there were no like lingering questions of like, did I do this right, or I got an error? Yeah.
I think the linear regression part, I think we can go over that a little bit. But I think
Yeah. So I'm just gonna run through a whole bunch of stuff. Go straight down into, there we go. So this one is like, in this case, there's a Prony series. This is like material science kind of way of like, how do you find like different time constants for something that is elastic but also viscous, so viscoelastic behavior. So the mechanical kind of metaphor for it is like a whole bunch of springs and dampers is how the material behaves. So if we know what the time constants are, like if it seems like we have certain time constants, we can figure out like what's the magnitude of that result, of like how big of an effect does each of those time constants have. So that's what we're trying to do here. So there's like this sigma 0 is kind of this 30, and then we're trying to find all these other like things here. All right, so we're going to load in the data, load text, and I'm just loading it to see like what happens. The first row has a label, like time, and actually, really what I like to do is look at the head of the data. So I can see, all right, I don't need this first. I need the data, but I don't need those parts. So I'm going to skip rows of 1. Then it's telling me that I can't convert 0 comma into a number. That's okay. I just need to tell it what the delimiter is. And I know we've done this before, but it never hurts to like kind of refresh how to load data into NumPy array. So once I skip that first row, add a delimiter, now I've got like data of like just time and stress. Data equals the first column is my time, the second column is my actual like stress values. And so now I want to make a z function, so like a big array that's only a function of time. It shouldn't have any values of stress in there because we're going to use the stress values to actually create the least regressions form. So z is going to be, let's try block. And I always forget, 1.78. 0.78 over 11. And I'm just going to check out what z looks like right here. All right, so right now, if I use block, it's just creating a long vector, but really what I want is an array, like a two-dimensional array. So I'm going to try this one, a v-stack instead. I like h-stack. No, all right, we'll do v-stack, but we'll take the transpose of it. So each column is going to be e to the negative t over that time constant. And it could be any function, but in this case, I just want to look at those like time constants. Time over 53. Over 411. This last one is just a constant, so inside my Z matrix, it should just be a column of all ones. I can get that in a few different ways. I could have like np.ones, the length of time, but here, because I'm using exponents, I'm just going to say that it's an exponent of time times 0. So for every value of time, multiply it by 0 and take e to the 0, so I just get 1. I just do that so it's a consistent kind of set of functions. You could also say time raised to the 0, ones, but let's look at z now. It's getting a little, like z is bigger now. If I zoom out, can I? Yeah, every row has these like 5 columns in it. Cool. So that's z, and if I have like constants that I already know, like if I just wanted to see these 5 constants, what the curve looks like, I could plug those in. So a guess is 2.91, 1.86, and 1.58, 2.08. And then what's the last one? 30.63. And I took z times a get, like times that set of coefficients. That's going to be that function, like sigma of t. And let's put this as like a red line. And it looks pretty good. How do I know that it's the best fit? Well, I would have to actually, because if I change this 1.6 to a 2, it still looks pretty good. So we still want to do like doing least squares. It's not that it is without a doubt the best function, but it's a repeatable, like if you use least squares, it's a repeatable method of saying like anyone with this data will get the same curve to go through that. So instead of just guessing what this should be, let's actually solve for it. And it's a linear algebra problem. So we say linalg solve of z transpose at z. And then my right hand side is z transpose at stress. And then I've got like my least squares curve, and we can see like what is. So the numbers that I get are like 1.9, 3.3, 1.1, 2.3, and then like around the same, like 30.6, same kind of numbers. Yeah.
What's the dot T? Something about here?
The dot T, that one's transpose.
Okay.
Yeah, so like take, and not everyone has done linear algebra. So like transpose is taking all the rows, turn them into columns. And for these like vectors, it doesn't matter. Transpose of a vector is still the same vector, but for yeah, and at least the way that we're trying to set this up is that every column is some function of t, like some evaluated function of t. So when you take the transpose here, this should be a 5 by 5 matrix when you say z transpose times z. Yeah, let's do. Let's just do this. Oh, come on, man. There we go. So if we just had like these three values here, 0 over 11, 1 over 11, e to the negative 1 over 50, e to the 0. And let's do like one more. So now I have 4 rows by 3 columns. If I say z transpose, it's going to be the same thing, but it'll be 3 rows by 4 columns. And again, this is a linear algebra thing that we're kind of learning through practice here rather than like diving deep. But when you multiply that z transpose times z, it's a 3 by 4 times a 4 by 3. So in this case, we'll get a 3 by 3 kind of output of the values in there. And we can take a look at that down here, right? Z dot t, dot t at z. And sure enough, I have 5 columns and 5 rows. And that stress has however many values in there. Let's see what this one is. 22. There we go. Z has 22 rows and 5 outputs, so when I take that Z transpose, now it's 5 by 22, and at the stress, then I just get 5 values. So kind of shrinking everything into just the least squares problem. There is from scipy dot linalg So if you solve a problem with like 23 equations but 5 unknowns, then it's over constrained. And so that's why we do a least squares of like, okay, well then what is the best fit? Like if I'm over constraining it, how do I minimize the error in each of the equations? So LST, this least square here, that should also give us the same output. And sure enough, it also gives us a little bit more information here. So in practice, you probably want to use like a least squares function like this, where it'll show you the solution, the residues. So how much error, the residue is kind of like how much error your function had. And then rank and singular values. Did we get any singular values? Rank 5, singular values. I don't know. Anyway, so that's kind of deep dive into that first problem of like, how do we do it? Did you get two lines for this one, or did that one work for this next part? 2 different slopes.
For the Euro,
Yeah.
I think I got the plot.
Okay.
I don't know. It's a good question.
Okay. Yeah. And so this is something I know in module 2, where we're looking like at a lot of data and kind of in fitting some functions. I mentioned to a lot of people, like, always plot your fit with your data. Like, you should never do a fit and just say like, okay, here the slope is 10 or something, or whatever values you're trying to pull out of this. Like these numbers don't mean anything if my plot doesn't match my data, because like I could have done I could make any kind of function I want, right? Like time to the 5th. Let's do a I might have issues with my what's wrong with this one? I was just trying to make up a function, but it's having trouble. Oh, I didn't take the transpose. That's why. So here, like I just sort of randomly said, like, all right, there's a sine function, there's a polynomial in there. I didn't keep track of like what the time constants were supposed to be, and like it goes through some of the data, but there's probably no reason to add a sine function, right? Like none of this data looks like a sine function. Yeah.
Trying to like guess that it is a sine function with the data and try to correlate that to the decimal.
Yeah, and like it's not wrong. You can always say like, oh, it's a combination of like sinusoidal functions. Like that's what Fourier transform is for. But in this case, it doesn't make sense to just say like there's a sine function with what was that period of 2 pi or something? Yeah, 2 pi seconds. Yeah, so instead of doing this one, stick to our original, like here are the time constants, let's solve for those like magnitudes of those exponential decays, and then we can go from there. Oh, and in this one we used pandas, right? Because pandas is a little easier to deal with this different stuff. Thinking about it. And I mean, at the end of the day, we're still going to use NumPy arrays to do least squares, like the linear algebra for least squares, but this one, it's a little easier to like segregate the data. Why doesn't it? I'm trying to use my autocomplete. Oh, it just hasn't run yet. Once it catches up. I don't know why it's taking so long. That one feels like an internet problem, but. All right, so now I've got it loaded up. Now I can say entity is, I think it's United States, like this. Man, it really slowed down. Something happened. Come on. I'm just trying to grab some data, man. There we go. All right, there's my US data. I think this one's Europe, like this. All right. I'm going to call it just T this time. Yeah.
You have to go in twice here with the brackets because it's is that how Magus operates, or is that more the fact that it's like a list? I guess it would be the same question. Is it like a list in case in a list? Or like, why would it go in twice into that energy?
Into this?
Yeah,
like,
energy, bracket energy.
So what I'm doing there is when I say energy entity like this, it's just giving me a list of like everything, like all the data, Africa, world, just like so all 5,065 rows. So if I say when is it equal to United States, I get a whole bunch of true and false statements that are Boolean operations. So really what I'm doing is creating like a Boolean to say, is it United States or not? So in this case, like Africa was the first one on there. We would see a bunch of trues and then everything else is false. So once I have this whole thing is just a Boolean operator. So like bool US. And then when I say energy of that thing, then it only gives me US energy values. So it's a way, and I was just like putting it all into one line in here with those bracket, but you could split it up into two steps of like, is it US, yes or no? And then plug that yes or no into the data to just grab those lines. And then the other thing that I'm kind of doing here is like I'm using pandas to kind of get my data into Python and organize it. Then I'm getting everything into NumPy arrays so that so I can just like do linear algebra on those NumPy arrays from there. And here, because each time value is the same, like for EU and US, I'm just going to make one Z matrix because it should be the same thing. And what did I do? A VStack before? VStack, and then I transpose it. So what does this function look like in, like I'm saying t to the 0, t minus split, t more than split. Like what is that polynomial, or what kind of function did I just plug in here? Let's try it out. Can't spell today. So what does this look like? I have a line. I said slope is 1, and then intercept is 2. My split is 1985, and at 1985 I'm going to add 3 to 1. So it goes from a slope of 1 to a slope of 4. So if this is a negative value, like if this is -1, we should get a straight line like this. So it had a slope of 1, then at 1985, the slope went from 1, subtract 1, so now we've got a flat line. But again, the goal is not so much like just guess random coefficients. I mean, it's good that we can plug in coefficients and see what the function looks like, but we're trying to do an actual least squares regression here. And Z can be anything for least squares regression. Let's try our LSQ, right? LSTSQ of Z, and then USE. Oh yeah, this would help. Z. What? 4 is different from 3. Why is it different from 3? I think I have to. What was the output here? One. So I just want that first output. Yeah, it's giving me like all 4 least squares stuff out. I forget how you can ignore that stuff. Yeah, I know there's a way that you can say like just throw stuff out. Oh, but we could just say this, like just give us the 0 output. I think that's what I'll do. At least if you want to follow along and use like least squares instead of creating your own least squares problem. So 1985 doesn't look like there's a huge like change in slope. And if I look at, trying to print. Started off as 2.7 and then decreased to 1.7. So just terawatt hours per year. So I could change it to a different day, right? 1980. Maybe something changed there. Year 2000. Yeah. That one I imported from SciPy's linear algebra. So if you want to use it, then you would import. You could say like scipy.lineal.lstsq or import from that whole library. Yeah, I bring that up because normally you wouldn't define your own linear algebra problem to define a least squares problem. You'd use like a least squares solver like this, but you get the same answer because it is doing the same thing, like taking Z transpose, multiplying by Z, and getting the answer. just a little cleaner to like keep them separate like this. Like here's my Z, my like assumed function, and then here's all the outputs I'm trying to match. So give me all the coefficients. It'll match that. But again, this can be anything we want it to be. I could say that it's a parabola but the slope changes in 1990. Or maybe the parabolic term changes in 1990. That one looks a little wacky, but yeah, I've seen some people do like more piecewise fits of like, we could say like every 10 years there's another split of like how does it connect each year. What's our first year? 65. We'll say every decade. Now it's starting to look pretty good. If we say every decade there was a change in slope, starting to match. We could say every year there was a change in slope, but now we're really overfitting the data. It's hard to extrapolate when you need every year to figure out what happened that year. Cool. Okay, so then next week, Monday, we'll take a look at project 4, the last project, and then we have Thanksgiving break at the end of that week. All right. So we'll have Monday, Wednesday, and then Friday, take it off. So we'll probably be trying to travel anyway. All right, thanks a lot.